Exercise 18E, Applications to Maximum and Minimum Problems. Almost every worded question relating to cubics or quadratics will eventually require you to find a turning point in some way or a point of inflection. Now that we have these skills to know about stationary points, i.e. when the derivative is equal to 0, we can find a stationary point. This will no doubt be able to help us find all of the answers that we possibly need to these sorts of questions. Whenever a question will say things like, find the maximum value, you know that's going to be either the turning point or possibly it might be the absolute maximums. In other words, it could be at either end of a cubic function of some kind. Otherwise, alternatively, usually see words like maximum as another one here. And I think later on we say what is, oh, look at this, we're still maximum and maximum. As soon as you start seeing the words maximum and maximum anywhere, or alternatively minimum, I'm surprised I haven't got a minimum example here, but if you're looking for maximum minimum, that's going to be solving for the derivative equaling 0. So that's just letting you know, in summary, that's exactly what this exercise is all about. Example 1. Find the maximum value of the product of two numbers x and 10 minus x. And of course, product here meaning multiply. So let's go and establish an equation where we have multiplied x and 10 minus x. So I've multiplied the two and now I've got myself an equation. I've just made the answer equal to y. I've just set y as whatever the answer might turn out to be. So this is, we want to find the maximum value. In other words, what we need to do is we need to establish a turning point. This is a quadratic. How can I tell it's a quadratic? Because we've got that x squared is the largest power there. It's quite likely you can almost draw what it's going to look like. I think from just by looking at it, it probably will look something like this, where 10 is here, 0 is here. I would dare say the turning point will be smack bang in between these intercepts, so it'll be 5. And if I substitute 5 into this equation, 5 times 5 is 25. So that's me solving this question without even using some calculus. But let's use the calculus to back myself up. So we're going to find the derivative, make that equal to 0, and solve for x. So we have found that x is equal to 5 when the derivative is equal to 0. Well, we also found it by drawing the picture. And now all we need to do is to substitute 5 into the original equation to be able to find what the y value is. 25. So the maximum value is going to be 25. Example 2. A rectangular sheet of cardboard, 50 centimeters by 40 centimeters, is to have square corners cut out so that it can be folded into a rectangular tray. Find the maximum volume possible for such a tray. So let's draw a little diagram. So if we cut out a square, each square is going to have the same size because a square has to have the same length. We don't know how much is being cut out of it, so let's label that as x. And then we'll draw a diagram of what it will look like when the rectangular box is folded up. So I have drawn my box, and you might notice that the dimensions now, they're not 40 and 50, they are 40 take away 2x and 50 take away 2x. But why? Well, that's because we cut out a little square that is x in length from either end of the box. So, for example, in this section where we've got 40 centimeters was for the whole length, well, for just this tiny bit, in other words, like the little flap that I fold up, that's going to be 40 take away one of the x from one end and the other x from the other end to get 40 take away 2x, as we have established here. As for the other end, the 50, well, for this section here, I've cut out an x on this side, cut out an x length on that side, so that means that side is going to be just 50 take away 2x. And when I fold it all together, the height is going to be the same height as the amount of x that I cut out from that square. So it's going to be x in height. So now what we need to do is we now need to work out the volume. The volume for a rectangular prism is going to be length by width by height. And you can imagine then, to find the maximum volume, I'm going to have to get the derivative of that function and make it equal to 0. But one step at a time, let's establish a volume equation. So we've established a volume formula. I've also expanded the brackets, for that will make the differentiation part much easier. To find the maximum volume, I just need to find the derivative of this, equal this to 0, and solve for x. So we made the derivative equal to 0, and then we solved it. Because we couldn't get exact brackets, I used the completing the square method to solve for x, and I got some very unfortunate square roots here. Just to give an idea, I also solved this on the CAS calculator as well. If the question stated decimal places, then we can use the CAS calculator. However, we should always assume in maths methods that we use the exact values. So the last step for this is then to substitute those x values into the original equation to see which one will generate the, in this case, maximum. So in other words, we want a y value that's the highest. This degree of substitution and expansion would be far beyond the course. I mean, you could do it theoretically, but it would be such a waste of time to do it by hand. So therefore, this one definitely suggests we should use a calculator. So let's solve it thusly. So we solved this on the CAS and we got two answers. One was 6,564.23 cubic centimeters and one was negative 564.23 cubic centimeters. We cannot have a negative volume, so therefore the largest is going to be this one here. It's worthwhile noting that a lot of students will assume that the larger x value, in this case the 15 plus the square root of 175 over 3 square rooted, would result in the larger maximum because they're running out of time, or just assume that a bigger x will mean a bigger y. Please remember that is not the case, as in this case, the correct x value is going to be 15 minus 175 square root that over 3, which is approximately 7.36. You could have also seen if this would result in a larger volume by looking at the original drawing. If you were just to approximate, so for example, let's just say x was equal to 7 or x is equal to 23, substitute back into the dimensions. 40 take away 2 times 7 versus 40 take away 2 times 23. 2 times 23 is going to get me 46. 40 take away 46 gets me a negative dimension. So just by doing that as an approximation with that image, I already know that it's going to be wrong. So that is another way that you can quickly speed up the process of this question. Example 3. A bank of earth has a cross-section as shown in the diagram. A cross-section, if you haven't seen this word before, just means cut in half. A bank of earth is also not one where you put money in. It's just like a hill or dump, if you like a less flattering term. a dump of earth, and in this case, earth being dirt. A hill of dirt, or a dump of dirt, or a bank of earth has a cross-section, or the cut in half part of this diagram, and it is defined by the equation y equals x squared over 400 times by 20 minus x, all in brackets, for x is some value between 0 and 20. We can see here that that is going to be 0 on this axis. We can see that the other x-intercept that we need to worry about is 20. Find the height of the bank where x is either of those values. So this is an old-fashioned substitution. So we have successfully substituted those values in. It's always best to try to keep your answer as a fraction where possible, especially if it hasn't said to limit it to a certain amount of decimal places, and you should always keep practicing up your technology-free skills. We can see as x increases to 15, we can see that we get a very large, or a much larger height for the bank of earth. And that indicates this picture here, where the height is about sometime here. It's a little bit more than halfway. B, find the value of x for which the height is a maximum and state the maximum height of the bank. As soon as we see the word maximum, and we can see here we probably need to find a turning point because that will be the maximum height of the bank. So we'll need to go and find the derivative, make that derivative equal to 0, solve for x, and then substitute that value for x back into the original equation. So we have found the derivative, and now we have made that derivative equal to 0, and we have solved for x. I would assume, therefore, we can see the original diagram that our choices of either x equals 0 or 1/10 minus 3 over 400x, one of those is going to result in a maximum. The diagram shows that when x is 0, it's actually very low, so the other value must be the one that we use. So the height of the mound of earth, or the bank of earth, we've substituted 40 over 3 into the original equation, and we got 80 over 27 meters. For C, find the values of x for which the derivative is either equal to 1/8 in 1 or to negative 1/8. So we need to go and substitute these for the derivative and solve for x. So let's start with that first substitution, that the derivative was equal to 1/8. So I solved for the quadratic by hand. You could have also solved this on the CAS calculator as well. The one thing, when I was completing the square, I got to two answers, either 20/3 take away the square root of 370 over 3, or x equals 20/3 plus the square root of 370 over 3. So rather than looking up at the calculator, I sort of made an approximation as to what was the square root of 370. I knew that the square root of 400 was 20, and I knew that 15 squared was 225. So it had to be somewhere in between those, and that's just because I know those two values. So using that in mind, if it's less than the square root of 20, then I know that both of those answers are going to end up being positive because 20 thirds is 6 2/3. So it has to be less than 20 thirds. So therefore, I know that both are positive. Why do I care that both are positive? Because the initial domain of the question, so if we go back, the initial domain has to be between 0 and 20. So therefore, both of those values exist. I have found the values of x for when the derivative is equal to 1/8. I'm now going to do something very similar to when the derivative is equal to negative 1/8. So now we have solved for the derivative is equal to negative 1/8. We only get one positive answer from this. We get the negative one. So if we wanted to do that off the top of our head, it's 5 times the root of 22 all over 3. The square root of 22 is going to be bigger than 4 and less than 5. So I'm going to substitute 4. 5 times 4 is 20. 20 over root 3 is equal to 0. So 20 over 3, take away 20 over 3 would be equal to 0. So if it's slightly bigger than that, it's going to be a negative number. And so therefore that is negative.